Hello everyone, we're going to go ahead and start into chapter 14, which I believe for you all is unit 9, unit 8 or 9 in terms of our content. We're going to focus on acids and bases. Now, I want to give you a heads up that this unit is going to have about 7 videos, but the majority of the video is actually going to be walking through examples and helping you to think through the process when you go and attack acid-base problems. So, let's go ahead and jump in, and we're going to look at our learning target for today. Of course, our usual learning target, our scores, we want to be at a 3.0 by the time we end everything. So, let's go ahead and get started. Hopefully you've taken the time to rate yourself and sort of look at this. Make sure that you review your notes, you summarize your notes as we go through this as well. I think that will help the concepts to stick a little bit better. And in class we'll talk about and go through some quick little video clips and examples that should hopefully help things to be a little bit clearer. Let's start it on now. Now, in Unit 3, we began talking about acids and bases, and we introduced a couple of definitions that we're going to use. The first one being Arrhenius, looking at the fact that acids produce hydrogen ions in concentration and bases hydroxide ions in concentration. Now, this was originally thought to be acceptable and enough information, but over time, it was found that there are other compounds that exhibit acidic or basic properties. And so this definition had to be expanded, and this was the job of Bronsted and Lowry. And they actually found that, according to what they were studying, that acids are just proton donors, or H plus ions donors, whereas bases are those that accept those protons. So looking at the example we have here, we have HCl as the acid, water here acting as the base. The HCl donates the hydrogen ion here, and this is what we're left with for our HCl, and we end up with our hydronium ion for, the base. Now, notice we've talked about this before. It's just the water molecule with the extra hydrogen attached, but this is the basis of what we're going to get with a lot of our Bronsted-Lowry acid-base reactions. Now, looking at the example, there are a couple of terms that you're going to need to be very familiar with. One is going to be what we call a conjugate base. Now, the conjugate base is everything that's left over after the acid donates away that proton. So, in the situation of what we're dealing with here, if I was to make this our acid, in this case HCl, this would be the example of our Cl minus. Okay? Now, the conjugate acid is the opposite of the base. So the base that received the proton is now slightly acidic, and this is what we call our conjugate acid. So we had our H2O, now it becomes H3O plus because it accepted that extra hydrogen as we're seeing it here attached. Okay, now we're going to need to understand that this is, again, the basis of what we're going to see for our Bronsted-Lowry acid-base reactions. We're going to see this in many different forms, so you want to make sure you understand what's happening here. Now, what makes a strong acid, or tells us that an acid is strong? What makes a strong acid is usually the ionization equilibrium lies far to the right, or it completely dissociates in water. Now, because it's going to completely dissociate, this is going to give us what we call a weak conjugate base. Okay, now, so that means out of our HCl, when it breaks down, it's going to form H plus, which we know is acidic, plus our Cl minus. Very, very weak. Why is it weak? It's coming from a strong acid, so it's going to be weak. Now, what about a weak acid? Well, the ionization equilibrium lies far to the left. So strong acid far to the right, and weak acid far to the left. This means that it's not going to dissociate much at all. It's usually going to be less than 5%. Okay? Now, because of the fact that it's coming from a weaker acid and the fact that it's actually holding on to that hydrogen ion as well as those that are staying together, it's going to be a much stronger conjugate base than we would have for our strong acids. So a good example of this, HF. We'll get very, very little of this. So most times what we actually will see is our H2O plus CN minus, but most of it's going to stay in this form. Okay. Now, here's a visual to sort of help it to make a little bit of sense. On our right, on our left, we have our strong acid here, which is actually pointing out complete dissociation or complete breaking down. There are none of these that are held together. Whereas on our weak side, we're looking at the initial versus how much of it actually breaks down overall. That very, very small amount of our acidic hydrogen and our conjugate base is telling us that it's going to be very, very weak. It's going to be a very strong attraction between these two. Okay? Now, just as a quick reminder, I wanted to point out our strong acids and strong base. When each of these breaks down, this is the dissociation process that we're actually going to associate with them. So these are 7 strong acids from hydroiodic acid, hydrobromic acid, and so forth down the list. You want to make sure you memorize these, and this is how they'll actually break down. Note here that with H2SO4 that it is not breaking down immediately into 2 hydrogen ions with a sulfate. It's actually breaking down into a hydrogen sulfate ion here. Okay? Now, it's a weak acid that actually can continue to contribute those additional protons because it has still a proton left here. Okay? Now, our strong bases, again, most of them being our group 1 elements and with their hydroxides, and there are 3 of them that we worry about in our group 2, calcium, barium, and strontium being strong. Now, I believe calcium and barium are actually, I think actually these 3 will sometimes only dissociate a small amount, but they are still our strong bases. Now, how do we describe acid strength? There are a couple of different ways. First is in terms of the Ka value, and I'll have a chart for you all that you can look at of common Ka values. The second is looking at the position of the equilibrium in terms of dissociation. Far to the right, we know it's strong. Far to the left, it's going to be weak. In terms of comparing the equilibrium concentrations between the two, for our strong acids, you notice that it's saying it's approximately the same. The hydrogen ion concentration is approximately the same as the initial concentration of the acid, whereas the weak acid is much, much smaller. That's why we have that double arrow here. Much, much smaller than that initial acid concentration. And last but not least, and this part is going to continue to play a role as we go throughout this unit, is the strength of the conjugate base when compared to that of water. For our strong acids, we're going to say that the conjugate base is much weaker than water. Whereas the weak acid is going to be much stronger than H2O. So that'll actually tell you whether or not your base or your acid will be water in that situation. But let's continue. Now, one of the reasons why we compare a lot of things to water is because water is what we call amphoteric, meaning it can be both acid and base. Now, with that, we need to consider how much water is being broken down. Is the acid breaking down more than water would, or is water breaking down more than the acid would? At 25 degrees Celsius, the Kw, or the water dissociation constant, should be equal to 1.0 times 10 to the 14th. Very, very, very small amount. But again, water self-ionizes. It breaks down just a little bit at a time. But no matter what solution we're dealing with, at 25 degrees Celsius, we must, in terms of our hydrogen ion and hydroxide ion concentration, when we multiply them together, we always need to come back to 1.0 times 10 to the, not 23rd, sorry, to the 14th. This is crucial. This is going to actually play out in how we determine Kb values and so forth of salt strengths a little bit later. Now, in terms of acid strength, we have 3 possible situations. First is that we end up with hydrogen ion concentration being equal to that of hydroxide ion concentration, and that's going to produce what we call a neutral solution. Note that we didn't say anything about pH at this point, we just said the point at which hydrogen ions and hydroxide ions are equal in terms of concentration. The second is where our hydrogen ion concentration is higher than that of hydroxide. That means that we're dealing with an acidic solution. And last but not least, hydroxide ion concentration is higher than hydrogen ions, and we end up with a basic solution. These are the three main situations that we will deal with throughout this unit, and make sure that you remember how we're actually going to put all that together to understand even pH in the next video that we're going to talk about. Now, into the concept check. This is into the practice part, so we're going to walk through a couple of examples, and feel free to fast forward or rewind or whatever you need to do to make sure you understand it. Now, in terms of our equilibrium constant, we need to know how an acid or how an acidic solution is going to actually respond inside of water. Well, there are a couple little tips that we can use. Looking at the reaction, we note that the water here is in a liquid state. What does that tell us? It's going to remain constant. So how would I write my equilibrium expression? Well, products over reactants. So I'm going to have K equals H3O plus, my hydronium ion concentration, times that of my conjugate base, for whatever the acid is, divided by the initial concentration of my acid. This is going to be consistent throughout all of the practice that we're doing. If the reaction's happening in water, water remains constant, so we don't consider that part into our equilibrium expression. Because of this fact, we're actually going to call this and use this as what we call our Ka value. Now, concept check. If the equilibrium lies to the right, the value of Ka is going to be what? Well, just like we did with equilibrium, if it's lying far to the right towards the products, that means that it has to be greater than 1. It's going to be large. Whereas if it falls to the left, that means that it's going to be small or less than 1. Same concepts bridging between equilibrium and acid-base. We're going to see a lot of comparisons between that. Now, if we're looking at water, the reaction given to us, if water is a better base than the conjugate base here, does that mean that the products or the reactants are going to dominate the equilibrium? If water is a better base than this, what does that mean? That tells us actually that the products are going to dominate here, which means that we're actually looking at a strong acid, okay? Because of the fact that it leans towards the products, that means we're dealing with a strong acid, and that the Ka value is going to be, it's going to be greater than 1. Everything's going towards the products, we end up with a greater value. Now, consider a 1 molar solution of HCl. Order the following from strongest to weakest base and explain why. Well, what do we know about HCl? Strong or weak acid. We know that it's one of our stronger ones, and we know that if it's strong, that means the conjugate base strength is going to be less than that of water. So we can already start looking and saying that this is going to be weakest. Oops, it says go from strongest to weakest. So we actually need to, that means it's going to be number 3. Now, next thing we have is water, or whether it's going to be our conjugate base from a weak acid. Well, we said that from a weak acid, it's actually going to be number 1. So that means water is going to be number 2. Let's check and see. Again, we're going to go through the process of thinking. How good is Cl- as a base? When we come out, strongest to weakest, our conjugate base from a weak acid is going to be stronger than water, which is going to be stronger than our chloride ion. This is the last one we're actually going to look at. Consider the following solution. We have a sodium salt, where our conjugate base is the anion from a weak acid. Which way is the reaction going to go? Well, since we know that it's going to that this is from a weak acid, that means we're not going to get much of it. So that means the equilibrium is going to lie to the left. Because we're not going to get much of this, that means it's going to have to lie to the left. We can't produce a whole lot of our weak acid if we only have a little bit of our conjugate base, original conjugate base from our weak acid remaining. All right. That's actually, we're going to pull this one up and we'll actually go through some more of these examples. I'll possibly produce another video so that you guys can look through and sort of look at them. I want to leave you with this problem to sort of work on your own. Considering the same solution, or same reaction, is the value of Kb going to be greater or less than 1 based on what we know? Take a moment. I want you to sort of reevaluate yourself. Where do you fall? And we'll pick this up at another time. Have a good evening.